Hello again. Are there any more questions?
Let's say I have a question.
Well,
So, how do we, let's say, fight with this problem? What do we do here?
excellent. And this will be a special topic which is called impedance matching. And I will talk on that, but not today. It deserves more time than we have today. But there are special techniques that can provide for impedance matching. Just I will make a small comment about that, which is not exactly a radio frequency solution. But for example, what if you had a transmission line with 50 ohms and you needed to deliver the whole power to a 100 ohm resistor? Well, there would be a very good solution if we had it in reality. But just imagine you had a transformer, like had you those small trains? When I was small, I had trains with a small transformer that have been running on my carpet, electric locomotives and so on. And there was a transformer transforming 220 volts into 12 volts, which were available for the trains. Because if I connected the trains into the socket directly, they would blast. But in fact, the transformer did an impedance matching. As you remember, a transformer that has a ratio of turns N. So if you get voltage 1, voltage 2, current 1, current 2, so we have voltage 2 is turns on the second side divided by turns on the first side, voltage 1, and current 2 is inversely, and the result then is that if you divide voltage and current on primary side and secondary side, you would get a transformation of impedance or resistance. So if I call it R1, which is voltage divided by current on the primary side, you would get, or R2, to have the same phase for all the equations, that would be N2 divided by N1 square R1. Which means that I can transform the impedance. If I insert a transformer, this 100, if I insert a proper transformer, which would be a transformer that has a square root of 2 transformation ratio, the circuit from here would look like a 50 ohm load, and the circuit after the transformer from this side would look like a 100 ohm coaxial cable. So a transformer is something that is capable of transforming impedances so that they match. But unfortunately, you would not easily build a transformer for 1 gigahertz. So there are other techniques that I will describe only later. So yes, this is the most important part for a radio frequency engineer, impedance matching. That's very important. It's not that important for, let's say, construction of locomotives or heavy current, because the dimensions there are very small when compared to the wavelength. So then you just work with DC and AC. But at high frequencies, you still have to think about standing wave ratio and impedance matching. Was that a good reply for now?
Yeah, of course.
Thank you. Are there Any more questions to this topic? Also now relax, because I will start something quite new. And I will start that without equations at the first stage. Remember, when we have been starting with coaxial cable, we have said we have a wave equation, and we just decided to say, okay, our propagation constant would be just equivalent to the propagation of wave number k, and in that sense we got a special kind of waves which is called transverse electromagnetic. But now let's think about other waves, and that what we will think about is something we have to relax and focus on that, because we have absolutely no opportunity to see that in our everyday life. Why? We are not used to high frequencies and small dimensions. So first, let's think about an experiment. What we have been investigating today, we have an interface between two different media. Let's this be a perfect conductor. And we have a wave, an electromagnetic wave, perpendicularly just reaching this boundary. And you remember, this is a perfect short, so that the reflection coefficient would be exactly -1. The whole power reflects back. Just interface, so that there is zero voltage or zero field strength at the interface. And we have a perfect standing wave ratio in the part from where the wave has been coming. Now just, have you seen Magnificent Seven? The movie?
Tarantino?
Well, that's another Magnificent Seven. There was a Magnificent Seven that was a remake of Akira Kurosawa film Seven Samurai, and there was the Magnificent Seven, and the John Sturges was the writer. Well, anyway, it was a film about 7 gunmen who have been hired by poor people to protect them from some guerrilla.
I think they are bandits who are looking for gold, and they just found a source nearby the place. I saw the movie.
Yeah, and there is one of those poor people wants to become also a gunman, and just the professional gunman makes him very unpleasant, because he asks him to clap his hands and just clap faster. And when he tries to do that at maximum velocity, he just puts his gun between those hands because he's very fast. That's the story about gunmen at the Wild West. But anyway, just imagine that we have hired one of those gunmen. For example, Anthony Quinn has been playing, and we will ask him to make a special trick. There is the wave incoming from somewhere in the universe, and our gunman, who is very, very fast, will not be equipped by a gun, but he would have a mirror, a perfectly conducting metallic sheet. And just when the wave enters here and reflects back, just in the moment when it gets here, he would put there another mirror. And as you know from the film, he is blindingly fast. So we will have the wave trapped in between two metallic parallel planes, and it would just reflect there and back forever, because we bought lossless metallic objects. We will catch 1/2 wavelength of the standing wave that will just reflect there and back, and we will have it in between those two walls forever. Fine, but not very useful technically. Now let us study the case. What happens there? Well, the wave travels for 1/2 wavelength, and that means a half wavelength is 1 pi as to the change of phase. So the wave travels and changes its phase against this place just by 1 pi, 1/2 of the circle. Now it reflects from a perfect metallic surface, as you know, that is an antiphase reflection. So it changes the phase by 1 more pi, so we've got 2 pi's. And it travels back. And it travels 1/2 of wavelength, which gets another pi of phase shift. And now it reflects and gets to the original position, but the reflection again is from a metallic object, and we have 1, 2, 3, 4 pi's, which is 2 whole circles. So after doing this, the wave gets in phase, because changing the phase by 1 full circle means that it's again in phase with the original one. So if we watch this as a resonator, it has the resonant condition, because by running the whole path, you just change the phase by n 2 pi, where n is an integer. So this could hold forever. However, if we do want to use it for some sound technical purpose, we would not be very happy. Well, we have trapped a wave, it is somewhere in. We can't test it because once we put there anything, we will damp it. So what's that good for? But now imagine that this perfect gunman, which is fast, and they shot with absolute coordinate precision, they shot anything. So he would be able to do what we want, and we will ask him, well, okay, we have the wave trapped there, it's just 1/2 wavelength, it's oscillating. So would you please move the mirror you hold in your hand so that it's still absolutely plane parallel, but it is a little bit more distant than 1/2 wavelength from the other. So we will a little bit increase the distance. Now the wave has a problem, because when running around the circle, the reflections still do 1 pi of phase shift. But the propagation is a little bit longer, and there is a little bit more than 1 pi of phase shift, which then means that the wave is not in phase, and after some reflections, it should destroy the whole wave by interference. Well, but that is not fully possible, because you can't destroy energy just... You can convert it into heat, you can convert it to mass if you have enough energy, but you can't destroy it. So something else must have happened by moving the mirror a little bit more distant. And this is quite interesting. If you move those two mirrors not a little bit more distant, I'm unable to draw it, only the gunman, and I have him here. So I will draw the case for another 2 mirrors that are more than 1/2 wavelength in distance. And now, this is interesting. In order to keep the property that the wave reflecting from the mirror is still in phase with itself and does not destroy by interference, the wave has nothing left but to propagate in this manner, it is a little bit tilted. So the wave, let's draw one ray, propagates by several reflections. And now, as the phase projects in this way, you can get the wave in phase with itself. So you have not destroyed the energy, but by moving the mirrors a little bit more distant, the wave that has been originally just bouncing up and down could be tilted and propagates along those two mirrors. But it does not propagate very quickly. While this velocity is still the velocity of light, it only projects to the way or direction of propagation by this part. So it is propagating somehow, but if you just move those mirrors a very tiny way from the half wavelength, it propagates very slowly. If you move the mirrors more distant, the wave gets more tilted and propagates faster. Okay, this is not the only strange thing you would see. Now, have you ever seen a velocity greater than the velocity of light? You would probably say no. And that's true. No material object, no information could propagate with a velocity faster than light. But there are things that do not exist in reality. But we can still recognize them, and those could propagate faster than light. And, well, I will show you now, with the exception of the camera, which has only 60 frames per second. But anyway, just imagine, can you see the intersection of this paper and this paper sheet? And the intersection moves. So if I move the paper, the intersection moves. The intersection is something we think about, but it's not a material object. So it can move faster than light. And I will show you, just by changing the angle, I am getting it to move faster and faster. And now be very patient and very concentrated, because in a few seconds you will see it propagating faster than light. At the moment that those two were close to parallel, the intersection propagated faster than light. And you have seen it now, possibly. But it's not anything that would propagate information or mass, because we only think about an intersection. It's not an object. So such a thing could propagate faster than light. Why I'm talking about that? Well, okay, just consider the phase. Just we would like to cut just a piece of those two mirrors guiding the wave in this manner, and we would like to cut just 1/2 wavelength. How long would that be? Well, we can find easily out. The ray that is reflecting up and down, of course, has a plane of constant phase, and it's perpendicular to the direction of propagation of the ray. So if we have the wave quite tilted, it propagates more or less along those two mirrors. The phase on the mirror would propagate with the velocity of light. But if we slow the wave by reflecting, just consider that this plane is more and more plane parallel to the reflecting mirror. So, in fact, if we come to the original case of two mirrors, just 1/2 wavelength, then the wave is just propagating this wave with equal phase planes parallel to the mirror, which means, in that case, that at a single time moment, there is the same phase on the whole mirror at any time. So if you would like to measure the velocity with which, say, a phase of 7 degrees propagates along that line, you would find it infinite here. Well, don't be worried. While the phase velocity reaches infinity, there is another velocity which is called group, and the group velocity reflects to propagation of information or energy. And we remember that the wave just travels there and back and there is no propagation. So we have a specific situation. We have two velocities here, a phase velocity and a group velocity. And if we multiply them, we get the velocity of light squared. So now we can see that there is a special situation where the phase propagates with infinite speed, but it carries no information. And at any other condition, we would have between those two mirrors the phase propagating a little bit faster than light on the cost of the energy and information propagating slower than the velocity of light. Again, if you put it this way, we have the speed of the group speed of propagation, information and energy, and it's only this projection of the velocity of light which propagates the ray. So the group velocity would be always smaller than the velocity of light, and on the other hand, the phase velocity would be greater than the velocity of light. Why do we bother with group and phase velocities? Especially, I understand, group velocity is the velocity with which propagates the information and energy. That's important anyway. But why do we bother to have another velocity introduced, which is the phase velocity? Well, because it's sometimes quite important, especially in impedance matching, which we will talk later, but you asked today, to have a transmission line of a certain phase length, say 25 degrees, 78 degrees, 220 degrees. But this reflects to the portion of the wavelength, and the wavelength is defined as the distance of 2 points on the surface of the line that differ 2 pi's in phase. And therefore the group velocity is important for propagating information and energy, but the phase velocity is important in order to establish lengths of the line for purposes like impedance matching. So we need to know both of them, and they differ. Now, there is another surprise we have with this kind of two-mirror line. The problem we do not know that from our everyday life is that if we had to learn that, we have the only experience with electromagnetic waves, and that's a kind of waves called light. Now, a typical wavelength of a visible light is some several hundreds of nanometers. This is, for example, a visible light, 530 nanometers. Well, now, to have the effect in effect, we would have to have two mirrors that are more or less half of that distance, each from the other. And we would have to look into that system, which is impossible. So we can't have direct experience with this. And it only came to man's side, or to man's invention at the time radio frequency waves have been created. So it's sometimes at the beginning of last century. At that time they have first developed high frequency circuits. There was important invention of the magnetron, which has been invented at several places. One of them was in Czechia, and that enabled to generate centimeter waves with the centimeter wavelength, and then all those effects became apparent. So then we could use that. And now we again return to two mirrors. So, okay, we have them in a position and the wave is propagating. But it's propagating slowly because it takes most of the time bouncing up and down and up and down and up and down. So we would like to fasten it. If it's faster, it would propagate better for us. Why losing time by oscillating up and down if we want it guided that way? So let's put the mirrors a little bit more distant. Then the wave becomes more tilted and the projection into propagation direction increases. So the wave propagates faster. So okay, so let's make it even more distant. Well, this perfectly works till we get the mirror to the distance of one full wavelength. Why? Okay. We had the original incoming wave that reflected and created a standing wave pattern. Now we put the mirror somewhere here so that we had one standing wave ripple in between the mirrors, and if we make it a little bit more distant, the wave there existed with this shape, just tilted to propagate. But if we exceed this point, we would get a strange situation, because we could have got here two ways. First, just by asking the gunman to catch not one half wavelength but two half wavelengths, or by catching one half wavelength and making the mirror slide to this position. So if we exceed the distance of one half wavelength, of one full wavelength, there will be two possibilities of propagation. One quite a lot tilted, let's say the black one, and the other which is only a little bit over its minimum distance, so it will propagate, let's say a red one, so it will propagate this way. Crazy, isn't it? Now we have to call that somehow, and in the vocabulary of transmission lines we call this modes. There are several modes of propagation, and unfortunately a wave could propagate in several modes, that is, with several velocities. So what would happen if you have a perfect set of mirrors and you just send a pulse on the input? Well, some part of the power of the pulse would propagate with this mode, some part would propagate with this mode. The result would be that you get not one pulse at the output, but two pulses. One is running faster, so it will reach the end earlier. The other would run slower, so it will reach the end slower. Well, this is nice, you got a multiplier of pulses. But what if you want to send, for example, a digital signal with some bit rate? Then you would be bound by the fact that you should distinguish some frequency in the input signal. If you send just one pulse and it produces two pulses at the output, it seems fancy, but what if you send this and the result at the input would be the first and the second wave would mix at the output, so that you would not be able to reconstruct the signal at the input. This is called dispersion, and it's typical for multimode propagation. So we have found out that in order for our two-mirror transmission line to be useful, we would have to keep the distance of the mirrors between one half wavelength and one full wavelength. And in that case, the wave would not propagate very fast. I mean, it will be a fraction of the velocity of light, still quite faster than a car or a plane, but it would not be that fast. And the second point, we have to consider that so far we have been using a monochromatic signal with fixed frequency and just moved the mirrors. But the same effect would be for a fixed set of mirrors with sweeping the frequency, because then higher frequencies would have lower wavelength, and therefore higher frequencies would propagate faster than lower frequencies. As you know, most of signals are not monofrequency, because a monofrequency signal carries no information. Mostly you use some kind of modulation. And the problem of such a kind of transmission line is that it's dispersive. That is, the velocity of propagation is dependent on the frequency of the signal. So if you create some complex modulation, then after some length of travel, the signal changes due to the dispersion of the line. You can, of course, use a very narrow band signal, but then you have a limited transmission capability as to information transmitted through that signal. So that's one of the problems that inherently come with this kind of lines. Just, we haven't been faced to this problem with a transmission line like a coaxial cable. At least in a lossless case, it has no dispersion, and it can carry the signal which even starts at DC. On the other hand, two mirrors are unable to propagate a DC signal. They have some window that starts at the distance of those two mirrors, which is one half of the wavelength of that signal. So there is a minimum frequency which gives rise to a propagating wave, and the lines are dispersive. To make the thing a little bit more funny or tricky, let us investigate another thing. But first, I have used a strange word, a mode which is something that guides the propagation. Now, to understand modes, it is again important to have some experience from everyday life. Does anybody of you play a guitar or a drum or violin?
Guitar a little bit.
Okay, then I will use a guitar example. So you have a guitar which has the important is not only the case, the important point at a guitar is the string. For this example, I will use a guitar with 2 strings only. So we have a string which runs through the body and is somehow fixed here. And there is several kinds of guitars. Of course, there are guitars that have no metal inserts here, but the classic guitar has some metal inserts that are placed here. And the metal insert is so spaced that it changes the tone of the string just by 1/2 tone. And playing chords or playing melody mostly is done by pressing the strings at proper locations by your left hand. Well, okay, and there is a special metal insert, number 12, which is in the half of the string length. My drawing is not very good, so let's say, okay, the 12 is somewhere here. And it has a very special property, because when you press the string there, you just send the tone 12 half tones up, which is 1 octave. So from E6 you get E7 and so on. Just 1